We can also use Taylor series to evaluate definite integrals to within some desired level of accuracy. In this case, suppose I want to find the integral from 0 to 1/2 of 1 over 1 plus x to the 7th. That is not something that we could find the antiderivative of based off of techniques we've seen in this class. So this problem in its original form is actually quite difficult. The suggestion here is to use Taylor series, and we're only asked to approximate the value rather than find it exactly. So let's think about how we could use Taylor series. In general, if I need to use Taylor series to evaluate a definite integral, I need to be able to come up with a series form for the integrand. In this case, that means we're looking at 1 over 1 plus x to the 7th. Oops, let me not put that in yellow. 1 over 1 plus x to the 7th. So notice that my interval is from 0 to 1/2. So that makes sense that I could focus on our known Taylor series that are centered at 0. So what I need to do is figure out how I can take this function and relate it to something on our list of the kind of known 6 functions. Well, to me, it most reminds me of 1 over 1 minus x. And to put it in that form, I could write it as 1 over 1 minus negative x to the 7th. Using function composition, then, I'm going to be able to say that the Taylor series here would be, in place of just x to the k, we'd have negative x to the 7th raised to the k. And I very much want to simplify that before moving on. So this is going to have terms negative 1 to the k, x to the 7k. That here is going to replace my integrand. And we've seen how to anti-differentiate power series, but perhaps we haven't really looked at definite integrals. So we'll see how that's slightly different than when we looked at the indefinite integral. My approach will be similar in terms of just anti-differentiating. So here I'm going to say that the definite integral we're trying to evaluate is equal to the definite integral of this sum that we found. And just like with our indefinite integrals, when I look at this, what I want to focus on is that this is an integral with respect to x. So this negative 1 to the k is a multiplicative constant. What I really want to do is anti-differentiate x to the 7k. And, whoops, I don't need to write the integral anymore. In doing that, we're going to get, so we still have negative 1 to the k. X to the 7k is now going to be x to the 7k plus 1, and we divide by 7k plus 1. So reversing the power rule. Whoops. And when we do that, because it is a definite integral, instead of just tacking on plus c like we've done with our indefinite integrals, I need to evaluate this from x equals 0 up to x equals 1/2. So that's just like we would do with anything. Plug in 1/2 and then subtract what you get when you plug in 0. But first I want to point out that when you plug in 0 here, you have the sum of 0 plus 0 plus 0 plus 0. So in fact, plugging in that lower limit of 0 is just going to give us 0. This means that instead of needing to express this as a difference, really what I'm doing here is I'm just going to plug in 1/2, and that series is going to equal our definite integral. So when I plug in 1/2, then we have terms negative 1 to the k, 1/2 to the 7k plus 1, all divided by 7k plus 1. And so what's important here is that if I could find the sum of this infinite series I've written here, that would be exactly equal to the definite integral we started with. But recall that we're not asked to find it exactly, and I don't know how to find the sum of that series. We're only asked to approximate it within some level of accuracy. So what we've seen so far is to approximate an infinite sum, generally we like to use a partial sum. And when we're given a desired level of accuracy, we need to determine how large n needs to be such that our nth partial sum is a good enough approximation. That's exactly what we talked about when we considered error bounds. So the first thing I want to point out here that's significant with regard to error bounds is that this is an alternating series. So I can use my information about the alternating series error bound to point out here we need the error here to be smaller than 10 to the negative 7th. And if you recall, the way that we could guarantee that that was true is to find n so that the upper bound on the error is small enough. So in this case, the upper bound on the error would be the absolute value of the next term. So I'm going to refer to this here as my a sub k. And we need a sub k plus 1 in absolute value, which is the upper bound on our, I should say n plus 1. I'm trying to determine the value of n. K is playing the role of my index. So we need the absolute value of a sub n plus 1 to be smaller than our desired error bound. And what I'm going to do here is actually just find what that absolute value is. So if I take the absolute value of my terms in this series, first of all, the negative 1 to the k drops away. And what I'm going to do is take both of these instances where I see a k and replace k with n plus 1. When I do that, I get 1/2 to the 7n plus 8 divided by 7n plus 8. To make sure it's clear, why do I have 8 instead of plus 1? Well, when I replace k with n plus 1, I distribute the 7. So there's 7n plus 7 plus 1. That's giving me the 8. So now we need this to be true. To be clear, this is not an easy inequality to solve for. I have an n in the exponent and in the denominator there. So this next step is something that I really did on a computer. You could likewise think about a calculator. If I want to find the smallest value of n for which this happens, and n equals 2 works. So point out here, this could be done with a calculator or a computer. And what I mean there is just try by plugging in values. Try n equals 1. Does that work? No, move on to the next. Try n equals 2. And we're stopping as soon as it works. And what does that mean? Because the goal here is to come up with an approximation, not a value for n. That means that we can take our sum above and we can replace the infinity with a 2. That's going to give us a good enough approximation. So my conclusion here is that the integral from 0 to 1/2 of 1 over 1 plus x to the 7th is roughly equal to the sum from k equals 0 to 2 of negative 1 to the k times 1/2 to the 7k plus 1 divided by 7k plus 1. And what would be a little bit nicer is to actually write out the terms that we get from that. So if you plug in 0, you're going to get 1/2. And then plugging in 1, we get minus 1 over 8 times 2 to the 8 plus 1 over 15 times 2 raised to the 15th power. So if we sum these three terms, what we found is that the value of those three terms added together would give me an approximation of this definite integral that's very, very, very close to the true value, right? The error is bounded above by 10 to the negative 7th. But again, more generally, you want to think about what this example demonstrates. So if I have integrals that I don't know how to evaluate by hand, I can still get a very good idea of the value of those definite integrals if I have an appropriate series that I can use to replace the integrand.